Hi, in this lecture, we discuss asymmetric cryptography. We particularly emphasize asymmetric encryption and key exchange, the Diffie-Hellman protocol. And we will show how to leverage elementary number theory to achieve these goals. Now, first, let's start with public key encryption. So public key encryption, or otherwise known as asymmetric encryption, consists in the following situation. There is a public key and a private key. Okay, so a particular entity creates the pair of keys and broadcasts the public key. Now, anybody with a plain text and the public key can encrypt, but only the entity that possesses the private key is able to decrypt. Okay, so this is the setup for public key encryption. Now, let's recap very briefly what is the security goal. So typically in previous lectures, as we've seen in previous lectures, we seek semantic security, which means that for any two given messages of their own choice, an adversary must be unable to decide with good advantage which one is encrypted in a particular ciphertext that is presented to them. Okay. Now, the very serious challenge posed by asymmetric encryption is that the adversary is able to encrypt. In particular, if the encryption is deterministic, then there is nothing stopping the adversary from encrypting both of the plain texts that constitute the challenge and compare the encryptions to the ciphertext that is presented to them. Okay, so somehow we need to make sure that the encryption of one plain text can lead to sufficiently many different ciphertexts, and that is something that intuitively doesn't seem very obvious. Okay, so how comes we could have one plain text leading to plenty of ciphertext, and somehow we're able to, for each of these given ciphertexts, decrypt back to the same plain text? And that's something that we're going to see in this lecture. So so the encryption that we, the first example of public key encryption is the RSA scheme, named after its inventors, Rivers, Shamir, and Edelman. So it relies on a trapdoor one-way function. So let's recap what that consists of. It has to be that for each input, it is easy to evaluate, okay, f, the function, is easy to evaluate just using the public parameters. So in particular, if there's a public key, okay, while using the public key and any other value that is public, it needs to be easy to evaluate. On the other hand, there needs to be it needs to be hard to invert unless someone knows the secret. So in particular, the secret key. So there needs to be some data that allows efficient inversion of this function. And without it, the inversion needs to be hard. Okay. And so the RSA one-way trapdoor function is the following. So assume that you have a public key that consists in a number that is the product of two primes p and q, and assume that you have a number e that is less than p minus 1, q minus 1. We're not going to get into the details of why this particular choice, but there are deep mathematical reasons for that. Now, the secret key consists in an integer d, which has the property that e times d mod p minus 1, q minus 1 equals 1. So this is called a modular inverse. So just if we accept that E and D have this property, then here is the evaluation of our trapdoor one-way function. You take x, raise it to the power e, and then reduce the result mod n. All of that requires only public parameters, okay? And that gives you the evaluation of your function. Now, what's the inversion looking like? Now, the inversion is you take a y and you raise it, this time, to the power d and reduce mod n. Now, this produces y to the d mod n, and if your y is x to the e mod n, then you will fall back on x. Now, there's a slight condition for that. X must not be divisible by p or q, okay? Again, these are there are mathematical reasons for that. But if you satisfy this property, which really isn't a big a deal as far as encrypting messages is concerned, then you will have this way to invert the RSA one-way trapdoor function using the key. Now let's just show an example with very small numbers. So let's say p equals 51 and q equals 53. And then these E and D have the property that E times D mod P minus 1 Q minus 1, which is 3120, is equal to 1. Now, if you take as input, for example, 65, which is not divisible by neither 61 or 53, you raise it to the power 17. That's a big number, by the way. But if you reduce mod 30 to 33, okay, you've got something that is less than 3,233. So it turns out, you can check with your calculator, this is 2,790. And if you take that number and you raise it to the power 2753, again, this alone is a very, very big number. But then if you reduce it, so you divide by 3233, take the remainder, and that magically ends up being 65. Okay, so you have inverted the one-way function. Okay, now how could that be used to encrypt messages? The obvious way is what people call sometimes textbook RSA. What does it mean? Well, you just use the one-way function as your encryption scheme, okay? One way being the encryption, the other way being the decryption, okay? So let's just present that, and then we'll say why this is a bad idea. So your encryption is a message that can be mapped into an integer that is between 0 and n, okay? And so you could want to check, of course, that this is not divisible by p and q, but when p and q's are large, then in fact, this is statistically not a problem. In fact, if it happened that your x here is divisible by p or q, then taking the GCD of that with n would actually break the crypto system. It would yield p and q, and then from that you would be able to find d, the secret exponent, for reasons again that I don't want to get into. But so we need to have p and q large enough so that whenever you draw an x at random, it is statistically impossible that it's divisible by p or q. Now, the encryption then becomes, well, applying the RSA function to this x, which is the mapping of the message. So x to the e mod n, and that's your ciphertext. And then decrypting is just raising that ciphertext to the power d, and you retrieve x, which is in one-to-one correspondence with the message. For example, you take the bits of the message and you look at the number that it gives you in binary representation. Okay, and this would be typically how you would do it. Big problem here is that this kind of encryption is deterministic. Okay, for every message you get only one ciphertext. Okay, and we've just said before that this yields a situation where we don't have semantic security. So somehow we need to design a better system where encryption of a given message can yield many different ciphertexts. Okay, we're going to use the one-way function of the RSA scheme, but we're going to have to be a little bit clever about it. And we're going to add what's called random padding. So for each message, we draw some random values, so a random sequence of bits, and we use a padding function, and I'm going to present an example of that in a minute, to produce an x, okay? So what it means here, and that x, of course, is a number between 0 and n. Now, what this means here is that for a given message, and a given two different values of the random value you draw, then you will get two different values, x's here. So the same message can lead to many different x's, okay? Now, it also needs to be, so first, the encryption then is raising of x to the power e and then reducing mod n, and that's your ciphertext. And then to decrypt, you first raise your ciphertext to the power d to retrieve x, and from x you invert the padding. Okay, so this padding function, of course, has to be invertible somehow, so that you retrieve both the message and the random value. Now, the random value can be discarded as part of the decryption process because nobody cares, right? What really matters is that you retrieve this. And of course, that for different values of the random string that you draw before feeding them to the padding function, you'll get different values of x and therefore different ciphertexts. Okay, now what kind of padding function can be used? So the standard to provide security is the optimal asymmetric encryption padding, OAEP. So how does this work? So you take your message, so you create a block that contains your message, then you put it next to a block of formatted data. So typically a bunch of zeros, okay? So enough zeros, but it could also have some other sort of formatting data with respect to the version of a particular algorithm that is being used. So here you can put some information that has to do with the format of the data. And here is your random value. So this is the rolling dice here that produces a random string that you put here. Now, what you do is you take the random value, you give it to a hash function, and the result is XORed bit by bit with this block consisting in the message and the formatted data. Again, think of it as a block of 0, okay? And then the output makes for, part of the padded value, but also you take it, hash it again, and then XOR it with the random values, and that gives you your second block here, okay? So all of that together is the outcome of your padding function, okay? So this, of course, is reversible. So if you do everything in reverse, okay, so take this block, hash it, XOR it with that block here, that gives you your random value, but also take your random value, hash it, XOR it with what you have here, and you'll retrieve your message and the formatting value, okay? Now, what's the point of this, first of all? So this is sort of a sanity check, okay? If you decrypt and somehow you don't retrieve your block of many zeros here, then chances are something went wrong, okay? My ciphertext maybe was corrupted, okay? So you learn, so by having a block of zeros, or at least having some formatting information here, you will learn that something went wrong somewhere along the line, okay? So that's good. So what this is doing is, basically, morally speaking, it takes the message and the randomness and it mixes the information in a reversible way to provide this X where all the information of the message and the randomness is there and it's well mixed. Now, there is a legitimate question one could ask here is, well, if all we care about is to produce many different X's for the same same plain text and different values of the randomness, then why don't we just take X to be this, okay? You can take M, put it side by side with the randomness, and that will produce you a different X every time you change the randomness, right? It will. However, there is a somewhat sophisticated attack against this kind of padding, and this kind of padding has been used, okay? So it's not that people saw at first that this was obviously insecure. It's actually not obvious at all, but there is a way to attack this kind of padding scheme. In terms of the security notions that we've discussed, this padding scheme is not CCA secure. It's not secure against chosen ciphertext attack. So there is a way to sort of generate a bunch of ciphertext and then have the adversary win the security game. In practice, it was also used to basically retrieve the key. And so I'll just want to say a few words. The way it works is one would just craft a bad ciphertext and send it to the server and get the server to deny, because when looking at the formatting after decryption, the server says, oh, yeah, there is a problem, and then sends a sort of piece of information saying, oh, you constructed an invalid ciphertext, okay? And with that information, many different ciphertexts, there is actually a way, very clever way, to retrieve the key. So OAEP is the right way to use random padding to make RSA secure. Now, let's talk about the alternative to RSA as far as public key cryptography is concerned. I mean, the main current alternative. And it relies on what's called a discrete logarithm problem. Okay, what is this problem? So we'll state it here in the way that requires the least amount of math. Okay, so let's P a prime number and let A and G be two numbers less than P. Now, the DLP, so discrete log problem, is the problem of finding an x such that A is G to the x mod P, okay? That might not sound very hard, but if P is large, this is actually difficult. So it can also be generalized. In particular, if for elliptic curves, and we'll say that we'll say something about that right at the end of this lecture. So what can we do with the discrete log problem? So the first example of the use of the discrete log problem in cryptography is the Diffie-Hellman key exchange mechanism. So it was actually designed before the RSA encryption scheme. So let's see what it consists of. So you have two players, Alice and Bob, and the goal of Alice and Bob is to create a shared secret key, okay, that they could be used they could use with a symmetric encryption scheme to communicate with confidentiality. The public parameters that everybody knows, including the adversaries, is a prime p and a g less than p. Then Alice and Bob independently choose some random numbers a and b, and Alice raise g to the power a and reduce mod p, so that gives you a number between 0 and p minus 1, and Bob does the same with b. And then Alice and Bob exchange their values, okay? So then Alice has g to the b, mod p, and Bob has g to the a, mod p. Then they can each, so Alice can raise g to the b to the a, and that gives her g to the ab, and reduce mod p. And Bob can do the same, raising Alice's value to the power b, reduce mod p. And then this common value is the shared secret key that they can use together. Now, a passive adversary listening to the communication, so the communication does not need to be secure, and that's really important here. The adversary could look at g to the b and could look at g to the a mod p. Now, if the adversary were able to solve the discrete log problem, that means that from g to the b, they would recover b. And in this case, from b and g to the a, they would be able to retrieve the value of the key. But it is presumed difficult for them to do so without the possibility to solve the discrete log problem. Now, there is also a public key encryption scheme that leverages the same sort of general strategy, okay? So we'll present it, although RSA really is the standard these days. So a public key consists in a prime P, and so that system is known as the ElGamal encryption scheme. So we have as a public key a P, so public parameters as a P is a prime, and G and H, which is less than P. And then, so H is equal to G to the X mod P, and so X is a private value here, okay? That is the private key. Now, to encrypt, one first draws a Y at random and computes C1, which is G, the public value, to the power Y, which is they just derived for this particular encryption and this only, and reduce it mod P, okay? And they also take H, so H, which is public, okay, so we're only dealing with public values here, raise it to the power Y, okay, and that is S, okay, they reduce mod P, and that's S. Now, this S goes into a hash function to produce a hash, we'll call that H, and this H is XORed with the message, and the pair C1 and C2, which is H XORed with the message M, is your ciphertext. So these two values together are the ciphertext. Now, how do you decrypt? You first Now, you assume to have the private key as the person who decrypts, of course. So you take that x and you raise C1 to the x mod p. And what do you get out of it? You get that value s. Now, because the hash function is known to everyone, you can take that s and retrieve the value h. And then what do? You take C2 and you XOR it with h. Now, h XOR m XOR h, the h's cancel each other. It's just like when you do the one-time pad, right? When you XOR with something and then you XOR again with the same thing, the original secret thing that you XORed your message with just disappears. So what it means is you retrieve m as C2 XOR h, okay? So that gives you the way to use the discrete log problem also to provide public key encryption, although RSA is definitely the most popular public key encryption scheme as of now. Now, I want to say something very brief about elliptic curves. Elliptic curves are very popular, especially when it comes to using, for example, the Diffie-Hellman key exchange mechanism. And but anything really that uses a discrete log problem can be used with elliptic curves. Now, we don't really in this lecture want to get too much into the mathematics of elliptic curves. So I just want to say really quickly a few words, and if that's way above your heads, just think that elliptic curves really are just like those Diffie-Hellman and ElGamal type schemes that we just presented. And so in a nutshell, elliptic curves are curves that have plenty of points, okay? So all the points that are on the curve, there is a way that you can add them up and subtract them, okay? So there is an algorithm that takes 2 points and produce another point on the curve for those special curves, for which I'm not giving many details here. And you can replace all these exponentiations that we described before, you know, when you had g raised to a certain power, with additions of a point with itself. Okay, so you trade a g to the a with a point added a times to itself. And if you work by analogy, you can you can repeat, you can sort of transfer all the schemes that use the discrete log problem with points in elliptic curves. And elliptic curves are very popular. So they have a lot of technical details, but fundamentally, they're doing, those schemes are the same as the ones that we were discussing before, where things are exponentiation. So the elements that we're using are exponentiations and then reductions mod p. So they can be adapted. So thank you very much for your attention.